Jai Hind everyone. I, Dr. Prashant Tripathi, going to Assistant Professor at Ajay Kumar Garg Engineering College in Electronics and Communication Engineering Department, going to present a topic based on multiple access for packet radio system. In this topic, we will discuss how the packets are transmitted according to a set of rule which is popularly known as protocol. So, first of all, we will discuss about random access. In random access, it is also known as contention method. No station is superior to another station and none is assigned the control over another. No station permits or does not permits another station to send. At each instant, a station that has data to send uses a defined procedure by which he decide whether he want to send or not to send. In random access, basically layered protocol system is introduced, which is based on OSI model, and this OSI model is known as Open System Interconnect Reference Model. In OSI model, the lower layer is physical layer, which take care of the actual physical transmission of packet by choosing the appropriate modulation scheme, bit rate, synchronization method, and so on. Basically, physical layer is the responsible for providing a interference between the device and the transmission medium. The issues concerning to packet access control or user access control are handled by the second layer, which is known as data link layer according to OSI reference model. Data link layer, or popularly known as DLL, it is responsible for node-to-node flow control, error correction, access control, etc. Basically, this data layer is subdivided into two layers. The lower sublayer is known as MAC layer, medium access control, and the upper sublayer is known as logic link control layer. So, by using these two layers, we control the flow of packets which are responsible for data flow. The multiple access protocol is divided into three parts: random access control protocol, controlled access protocol, and channelization protocol. Further, this random access protocol is divided into four parts: Aloha, CSMA, CSMA-CD, CSMA-CA, which we will discuss in this presentation. Controlled access protocol is divided into three parts: reservation, polling, and token passing. Channelization protocol is again divided into three parts: FDMA, TDMA, and CDMA, which we are well known from these three topics. In this, the channels are shared on the basis of frequency, time, and code. So, in this presentation, we will discuss about the random access protocol, and in this random access protocol, we will discuss about Aloha, CSMA, CSMA-CD, and CSMA-CA. So, first we will discuss about Aloha. In Aloha, which is popularly known as pure Aloha, is developed by University of Hawaii in 1970s, and it is used for packet radio network. In this Aloha system, the sender S transmit a packet at any time, hoping no collision will occur. S find out whether the transmission was successful or experience a collision by waiting for an acknowledgement broadcast from the destination station. If the transmitter receive an acknowledgement signal from the receiver within a time period t, then the transmission is successful. Otherwise, if there is no acknowledgement within the time duration t, then the transmitter assumes that there was a collision and the packet was lost after colliding with a packet of another transmitter. In this situation, if there was a collision, the transmitter S retransmit after some time the same packet. For example, here we have shown the transmission system of Pure Aloha. We have 4 stations, station 1, 2, 3 and 4. In this condition, station 1 transmitted its frame 1.1 and no other station is transmitting. But if in this situation, when the station 1 transmitted another frame 1.2 and in same time the station 2 is also transmitting, 3 is also transmitting and 4 is also transmitting, then there will be a collision, and due to this collision the packet will not reach at the destination. In this condition, the stations has to retransmit their packet after waiting the acknowledgement from the receiver. Similarly, at this duration, there is only one packet from source 3, so there is no chance of collision. What happened when the more than one transmitter transmit their packet is this situation is shown in this presentation. For example, at a time t, the station 1 is transmitting its packet, which is represented here by MS1 packet. When the mobile station 2 transmit its packet and after some time the mobile station 3 is transmitting their packet, then there is a collision at time t plus t. When this collision occur, the transmitter wait for a time, random time, and after waiting a random time, the mobile station 2 and mobile station 3 will retransmit their packets. So, this process is known as Pure Aloha process. Presentation in this slide, we have shown the vulnerable time for Pure Aloha protocol. What happens? Suppose B is transmitting its packet and again at time t, the station A starts its transmission. What happened? As it is clear from this figure, there will be a collision in between these two packets. To avoid collision, this packet A must start from here. Only then there is less probability of collision. So, to avoid the collision, the vulnerable time must be twice of frame time. If this condition occur, then there is no possibility of collision. Now, we will calculate the throughput of Aloha. As we know that throughput is the maximum capacity. So, to compute the throughput of Aloha, we assume that the packet length is represented by t in duration and the probability that n packet arrive in time 2t is Pn. If two packets of length t arrive in time greater than 2t, they didn't collide. And in this condition, the probability Pn is given by 2z power n e to the power minus 2g by factorial n, where g is the normalized offered traffic load for the channel. The probability that a packet is successfully received without no collision is computed by putting n equals to 0 in this formula. When we put n equals to 0, we will get 2g e to the power minus 0 by factorial 0, and this will become e to the power minus 2g, and the throughput S equals to g into p probability at n equals to 0, which we have computed e to the power minus 2g. So, putting this value, we will get S equals to g into e to the power minus 2g. For maximum throughput, which occurs at g equals to half, when we put g equals to half, we will get 1 upon 2e, and this value comes 0.184. So, in case of pure Aloha, the efficiency, or we can say that maximum throughput is 0.184. To improve the efficiency of Aloha, another technique is proposed, another protocol is proposed, which is known as slotted Aloha. In slotted Aloha, the time is slotted. In this protocol, in this slotted Aloha, the packets are transmitted only in a particular time slot, and this slot length is equals to packet length, which is shown in this figure. Here, the time is divided into slots, slot 1, slot 2, slot 3, slot 4, and so on. And if any station want to transmit their packet, he can use only the time slot available for them. So, packet transmission can start only at the beginning of a slot, and this basically reduces the probability of collision. In pure Aloha, if packet 1 is almost finished, when it collides with just starting the packet 2, collision can last nearly 2t. In slotted Aloha, two packets can collide only when both are starting at the same time period or same time slot. For example, here station 1 is transmitting in this time slot, and in no other station is transmitting in this time slot. So, the probability of collision is 0. But if both these two stations start transmitting in time slot 2, then there will be a collision and the data will last. Similarly, in times 3, when station 1 and station 4 are transmitting their packet, then there is a probability of collision. So, in slotted Aloha, the probability of collision occur only when the two or more stations transmit their packet at the same time slot. For example, in time slot 1, only one mobile station is transmitting, but after some time, mobile station 2 and 3 both are transmitting at the same time slot, then there will be collision, and when collision will occur, the mobile station 2 and 3 wait for a random amount of time and then they retransmit their packet after some time. So, this is the process of slotted Aloha. Now we will again compute the throughput of slotted aloha. Again, we have computed earlier that probability of no collision is e to the power minus g. Throughput is normalized g into p2 probability of n equals to 0. This will become g into e to the power minus g, and we know that in slotted aloha case, the maximum throughput occur at g equals to 1. So, when we put this value of g in this equation, we will get S max equals to 1 by epsilon, and after calculation we will get the maximum throughput is 0.368, which shows that in case of slotted aloha, the throughput is maximum as compared to pure aloha. So, in this case, we can see that the efficiency of slotted aloha is larger than the pure aloha. The same statement is shown in this presentation, as it is clearly shown that if we increase the traffic load, in that conditions also the throughput of slotted aloha system is larger than the pure aloha system. For value at half, the throughput of pure aloha is 0.184, but for slotted aloha, the value is larger than 0.184 for a traffic load of half. So, in each condition, the throughput of slotted aloha is larger than the pure aloha. In these two protocol, a comparison is provided in this slide, and it is clearly that in pure aloha at any time can be sent the data in any station, but in slotted aloha each station can send their data only at a particular time slot. In pure aloha, the time is not globally synchronized, but in slotted aloha, the time is synchronized. Pure aloha is continuous time, but slotted aloha is discrete time. In pure aloha, as we have seen that vulnerable time is twice of frame time, but in slotted aloha, the vulnerable time is time of a frame. The throughput of pure aloha is 0.184, while which is 18%, while in case of slotted aloha, its value is 37%. So, these are the main differences between pure aloha and slotted aloha. Now, we will discuss about CSMA, which is known as Carrier Sense Multiple Access Protocol, as compared to aloha protocol. Basic improvement in CSMA protocol over aloha protocol is, first, in CSMA protocol, the station sense the channel. It means before transmitting the data over the channel, the station or transmitter listen the channel, whether channel is transmitting some information or it is ideal. If channel is not transmitting, if the channel is not transmitting, then the station will transmit, and if the channel is busy, then the station will wait for a time, and when the channel become available free, the station will transmit. A brief working is shown in this figure. Mobile station senses the channel. It found that the channel is free, then it will transmit its data. Similarly, mobile station 2 senses the channel. The channel is free, the mobile station will transmit. Similar cases occur with mobile station 3, but in this case, the mobile station 6 and mobile station 7 are sensing the channel at the same time, and they found that the channel is free, and both are starting their transmission at same time, then definitely there will be collision. So, in this case, there is also a possibility of collision. Now, the CSMA protocols are divided into non-persistent CSMA and persistent CSMA. The non-persistent CSMA are divided into unslotted non-persistent CSMA and slotted non-persistent CSMA. Again, persistent CSMA is divided into one persistent CSMA and p persistent CSMA, which we will see in the next slide. In persistent method, the source continuously senses the channel, and when it found that channel is free, it transmit their data. But in non-persistent method, the source sense the channel. If the channel is busy, it wait for a time, and after some time it again sense the channel, and if the channel is free, then it will transmit, otherwise it again wait for a random amount of time. In p persistent CSMA, the channel continuously senses the source continuously senses the channel, and if it found that the channel is free, it will transmit their data with a certain probability. So, this is known as p persistent CSMA protocol. In this flow diagram, all the CSMA protocols are shown in this figure. When one persistent CSMA, the source senses the channel. If the channel is busy, it will sense continuously, and if the channel is free, the station can transmit. In non-persistent, if the channel is busy, the source will wait for a random amount of time, and again after a random amount of time it will sense the channel. If the channel is free, then the station can transmit. In p persistent CSMA, the source senses the channel. If the channel is busy, it continuously senses the channel, and if the channel is free, then it wait is a certain amount of time, wait for a slot, and then it transmit their data with a probability of p. So, in non-persistent CSMA protocol, if the medium is ideal, the source transmit immediately. If the medium is busy, it will wait a random amount of time, and then it go to step 1, that is, if the medium is ideal, transmit immediately. In one persistent CSMA protocol, if the medium is ideal, transmit immediately. If the medium is busy, continue to listen until the medium become idle and then transmit immediately. In p persistent CSMA protocol, slotted time required. If the medium is ideal, transmit with probability p, or delay till next time slot with probability 1 minus p. If transmission was delayed by one time slot, then again station go to step 1, that is, if the medium is ideal, transmit with probability p, or delay till next time slot with probability 1 minus p. If the medium is busy, continue to listen until medium become idle, then go to step 1. P persistent CSMA is a good trade-off between non-persistent and one persistent CSMA. Next is CSMA-CD, which is known as Carrier Sense Multiple Access Protocol with Collision Detection. In CSMA, if two terminals begin sending packets at the same time, each will transmit its complete packet even if collision is taking place. And in this situation, there is a wastage of time as well as wastage of medium. So, there is a solution, and this solution is known as CSMA-CD. In CSMA-CD, if the medium is idle, then the source transmit their packet. If the medium is busy, source continue to listen until the channel is idle. Then the source transmit their packet. When a collision detect during the transmission is stopped and wait for a random amount of time, and then again the packets will transmit. So, in this condition, when a collision is detected, the transmission will be stopped. Next protocol is CSMA-CA, which is known as CSMA with collision avoidance. In collision avoidance, the back off before collision. It means CSMA-CA is used in wireless Wi-Fi network and it is similar to CSMA-CD, but the difference is that in CSMA-CD, the transmission is stopped after a collision, but in CSMA-CA, the transmission is stopped before the collision. Working of CSMA-CA. First, it checks the status of medium. If the medium is busy, the station waits until the medium become idle. If the channel is idle, then the station wait for an inter-frame gap amount of time and then send the frame. Third step, after sending the data frame, CSMA-CA set as a timer. In the end, the station wait for positive acknowledgement from the receiver. If positive acknowledgement is received before the expiry of timer, then it is a successful transmission. Otherwise, the station wait for a back off time and restart their transmission. The working is explained in this figure. This is the mobile station A frame. Mobile station B and C senses the medium. Medium is busy, then it wait and again it send its frame. Here mobile station C again senses the medium, but it found that the B is transmitting their frame, so it will not transmit their frame. The presentation is prepared with the help of these two books. Thank you.